Preface and Introduction to A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melanie T. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Preface and Introduction. Preface to the 4th edition. Since the 3rd edition of the present work issued from the press, the 19th century has run its course and finished its record. A new era has dawned, not by chronological prescription alone, but to the vital sense of humanity. Novel thoughts are rife, fresh impulses stir the nations. The soughing of the wind progresses, strikes every ear. The old order changeth, more and more swiftly as mental activity becomes intensified. Already many of the scientific doctrines implicitly accepted 15 years ago begin to wear a superannuated aspect. Dalton's atoms are in the process of disintegration. Kirchhoff's theorem visibly needs to be modified. Clerke-Maxwell's medium no longer figures as an indispensable factotum. Absolute zero is known to be situated on an asymptote to the curve of cold. Ideas, in short, have all at once become plastic, and none more completely so than those relating to astronomy. The physics of the heavenly bodies, indeed, finds its best opportunities in unlooked-for disclosures, for it deals with the transcendental conditions, and what is strange to terrestrial experience may serve admirably to expound what is normal in the skies. In celestial science especially, facts that appear subversive are often the most illuminative, and the prospect of its advance widens and brightens with each divagation enforced or permitted from the straight paths of rigid theory. This readiness for innovation has undoubtedly its dangers and drawbacks. To the historian, above all, it presents frequent occasions of embarrassment. The writing of history is a strongly selective operation, the outcome being valuable just in so far as the choice what to reject and what to include has been judicious, and the task is no light one of discriminating between barren speculations and ideas pregnant with coming truth. To the possession of such prescience of the future as would be needed to do this effectually I can lay no claim, but diligence and sobriety of thought are ordinarily within reach, and these I shall have exercised to good purpose if I have succeeded in rendering the 4th edition of A Popular History of Astronomy During the 19th Century not wholly unworthy of its place in the scientific literature of the 20th century. My thanks are due to Sir David Gill for the use of his photograph of the great comet of 1901, which I have added to my list of illustrations, and to the Council of the Royal Astronomical Society for the loan of glass positives needed for the reproduction of those included in the 3rd edition. London, July 1902. Preface to the 1st edition. The progress of astronomy during the last 100 years has been rapid and extraordinary. In its distinctive features, moreover, the nature of that progress has been such as to lend itself with facility to untechnical treatment. To this circumstance the present volume owes its origin. It embodies an attempt to enable the ordinary reader to follow, with intelligent interest, the course of modern astronomical inquiries, and to realize, so far as it can at present be realized, the full effect of the comprehensive change in the whole aspect, purposes, and methods of celestial science introduced by the momentous discovery of spectrum analysis. Since Professor Grant's invaluable work on the history of physical astronomy was published, a third of a century has elapsed. During the interval, a so-called new astronomy has grown up by the side of the old. One effect of its advent has been to render the science of the heavenly bodies more popular, both in its needs and in its nature, than formerly. More popular in its needs, since its progress now primarily depends upon the interest in and consequent efforts towards its advancement of the general public. More popular in its nature, because of the kind of knowledge it now chiefly tends to accumulate is more easily intelligible, less remote from the ordinary experience, than that evolved by the aid of calculus from materials collected by the use of the transit instrument and chronograph. It has thus become practicable to describe, in simple language, the most essential parts of recent astronomical discoveries, and, being practicable, it could not be otherwise than desirable to do so. The service to astronomy itself would not be inconsiderable of enlisting wider sympathies on its behalf, while to help one single mind towards a fuller understanding of the manifold of works which have in all ages irresistibly spoken to man of the glory of God, might well be an object of no ignoble ambition. The present volume does not profess to be a complete or exhaustive history of astronomy during the period covered by it. Its design is to present a view of the progress of celestial science, on its most characteristic side, since the time of Herschel. Abstruse mathematical theories, unless in some of their more striking results, are excluded from consideration. These, during the 18th century, constituted the sum and substance of astronomy, and their fundamental importance can never be diminished, and should never be ignored. But as the outcome of the enormous development given to the powers of the telescope in recent times, together with the swift advance of the physical science, and the inclusion by means of the spectroscope of the heavenly bodies within the domain of its inquiries, much knowledge has been acquired regarding the nature and condition of those bodies, forming, it might be said, a science apart, and disembarrassed from immediate dependence upon intricate and, except the initiated, unintelligible formulae. This kind of knowledge forms the main subject of the book now offered to the public. There are many reasons for preferring a history to a formal treatise on astronomy. In a treatise, what we know is set forth. A history tells us, in addition, how we came to know it. It thus places facts before us in the natural order of their ascertainment, and narrates instead of enumerating. The story to be told leaves the marvels of imagination far behind, and requires no embellishment from literary art or high-flown phrases. Its best ornament is unvarnished truthfulness, and this at least may confidently be claimed to be bestowed upon it in the ensuing pages. In them unity of treatment is sought to be combined with a due regard to chronological sequence, by grouping in separate chapters the various events relating to several departments of descriptive astronomy. The whole thing is divided into two parts, the line between which is roughly drawn at the middle of the present century. Herschel's inquiries into the construction of the heavens strike the keynote for the first part. The discoveries of sunspot and magnetic periodicity, and of the spectrum analysis, determine the character of the second. Where the nature of the subject required it, however, this arrangement has been disregarded. Clearness and consistency should obviously take precedence of method. Thus, in treating of the telescopic scrutiny of the various planets, the whole of the related facts have been collected into an uninterrupted narrative. A division elsewhere, natural and helpful, would have been purely artificial, and therefore confusing. The interests of students have been consulted by a full and authentic system of references to the sources of the information relied upon. Materials have been derived, as a rule with very few exceptions, from the original authorities. The system adopted has been to take as little as possible at second hand. Much pains have been taken to trace the origin of ideas, often obscurely enunciated long before they came to resound through the scientific world, and to give each individual discoverer, strictly and impartially, his due. Prominence has also been assigned to the biographical element, as underlying and determining the whole course of human endeavour. The advance of knowledge may be called a vital process. The lives of men are absorbed into and assimilated by it. Inquiries into the kind and mode of the surrender in each separate case must always possess a strong interest, whether for study or for example. The acknowledgments of the writer are due to Professor Edward S. Holden, Director of the Washburn Observatory, Wisconsin, and to Dr. Copeland, Chief Astronomer of Lord Crawford's Observatory at Dunlick, for many valuable communications. London, September 1885. Introduction. We can distinguish three kinds of astronomy, each with a different origin and history, but all mutually dependent and composing in their fundamental unity one science. First, in order of time, came the art of observing the returns, and measuring the places, of the heavenly bodies. This was the sole astronomy of the Chinese and Chaldeans. But to the vigorous Greek mind added a highly complex geometrical plan of their movements, for which Copernicus substituted a more harmonious system, without as yet any idea of a compelling cause. The planets revolved in circles because it was their nature to do so, just as laudanum sets to sleep because it possesses a virtuous dormitiva. The first and oldest branch is known as observational or practical astronomy. Its business is to note facts as accurately as possible, and is essentially unconcerned with schemes for connecting those facts in a manner satisfactory to the reason. The second kind of astronomy was founded by Newton. Its nature is best indicated by the term gravitational, but it is also called theoretical astronomy. It is based on the idea of cause, and the whole of its elaborate structure is reared according to the dictates of a single law, simple in itself, but with the tangled web of whose consequences can be unravelled only by the subtle agency of an elaborate calculus. The third and last division of celestial science may properly be termed physical and descriptive astronomy. It seeks to know what the heavenly bodies are in themselves, leaving the how and the wherefore of their movements to be otherwise answered. Now, such inquiries became possible only through the invention of the telescope, so that Galileo was, in point of fact, their originator. But Herschel first gave them a prominence which the whole progress of science during the 19th century served to confirm and render more exclusive. Inquisitions begun with the telescope that have extended and made effective in unhoped-for directions by the aid of the spectroscope and photographic camera, and a large part of our attention in the present volume will be occupied with the brilliant results thus achieved. The unexpected development of this new physical celestial science is the leading fact in recent astronomical history. It was out of this regular course of events, in the degree which it has actually occurred, it could certainly not have been foreseen. It was a seizing of the prize by a competitor who had hardly been thought qualified to enter their lists. Orthodox astronomers of the old school looked with a certain contempt upon observers who spent their nights in scrutinizing the faces of the moon and planets rather than in timing their transits, or devoted daylight energies not to reductions and computations, but to counting and measuring spots on the sun. They were regarded as irregular practitioners, to be tolerated perhaps, but certainly not encouraged. The advance of astronomy in the 18th century ran in general an even and logical course. The age succeeding Newton's had for its special task to demonstrate the universal validity and trace the complex results of the law of gravitation. The accomplishment of that task occupied just 100 years. It was virtually brought to a close when Laplace explained to the French Academy, November 19th, 1787, the cause of the moon's accelerated motion. As a mere machine, the solar system, as far as it was then known, was found to be complete and intelligible in all parts, and in the Mécanique Céleste, its mechanical perfections were displayed under a form of majestic unity, which fitly commemorated the successive triumphs of analytical genius over problems amongst the most arduous ever dealt with by the mind of man. Theory, however, demands a practical test. All its data are derived from observation, and their insecurity becomes less tolerable as it advances nearer to perfection. Observation, on the other hand, is the pitiless critic of theory. It detects weak points, and provokes reforms which may be the beginnings of discovery. Thus theory and observation mutually act and react, each alternately taking the lead in the endless race of improvement. Now while in France, Lagrange and Laplace were bringing the gravitational theory of the solar system to completion, work of a very different kind, yet not less indispensable to the future welfare of astronomy, was being done in England. The Royal Observatory at Greenwich is one of the few useful institutions which date their origin from the reign of Charles II. The leading position which it still occupies in the science of celestial observation was, for near a century and a half after its foundation, an exclusive one. Delambre remarked that, had all other materials of the kind been destroyed, the Greenwich records alone would suffice for the restoration of astronomy. The establishment was indeed absolutely without a rival. Systematic observations of sun, moon, stars, and planets were during the whole of the 18th century made only at Greenwich. Here materials were accumulated for the secure correction of theory, and here refinements were introduced by which the exquisite accuracy of modern practice in astronomy was eventually attained. The chief promoter of these improvements was James Bradley. Few men have possessed in equal degree with him the power of seeing accurately and reasoning on what they see. He let nothing pass. The slightest inconsistency between what appeared and what was to be expected roused his keenest attention, and he never relaxed his mental grip of a subject until it is yielded to his persistent inquisition. It was to these qualities that he owed his discoveries of the aberration of light and the nutation of the earth's axis. The first was announced in 1729. What is meant by it is that, owing to the circumstances of light not being instantaneously transmitted, the heavenly bodies appear shifted from their true places by an amount depending upon the ratio which the velocity of light bears to the speed of the earth in its orbit. Because light travels with enormous rapidity, the shifting is very slight, and each star returns to its original position at the end of a year. Bradley's second great discovery was finally ascertained in 1748. Nutation is a real-life nodding of the terrestrial axis produced by the dragging of the moon at the terrestrial equatorial protuberance. From its results an apparent displacement of the stars, each of them describing a little ellipse about its true or mean position in a period of nearly 19 years. Now, an acquaintance with the fact and the laws of each of these minute irregularities is vital to the progress of observational astronomy, for without it the places of the heavenly bodies could never be accurately known or compared, so that Bradley, by their detection, at once raised the science to a higher grade of precision. Nor was this the whole of his work. Appointed Astronomer Royal in 1742, he executed during the years 1750 to 1762 a series of observations which formed the real beginning of the exact astronomy. Part of their superiority must, indeed, be attributed to the cooperation of John Baird, who provided Bradley in 1750 with a measuring instrument of till then unequalled excellence. For not only was the art of observing in the 18th century a peculiarly English art, but the means of observing were furnished almost exclusively by British artists. John Doland, the son of a Spitalfields weaver, invented the achromatic lens in 1758, removing thereby the chief obstacle to the development of the powers of refracting telescopes. James Short of Edinburgh was without a rival in the construction of reflectors. The sectors, quadrants, and circles of Graham, Bird, Ramsden, and Carey were inimitable in the continental workmanship. Thus practical and theoretical astronomy advanced on parallel lines in England and France respectively, the improvement of their several tools, the telescope and the quadrant on the one side, and the calculus on the other, keeping pace. The whole future of the science seemed to be theirs. The cessation of interest, through a too speedy attainment of the perfection towards each spurred the other, appeared to be the only danger it held in store for them. When all at once a rival stood by their side, not indeed menacing their progress, but threatening to absorb their popularity. The rise of Herschel was the one conspicuous anomaly in the astronomical history of the 18th century. It proved decisive of the course of events in the 19th. It was unexplained by anything that had gone before, yet all that came after hinged upon it. It gave a new direction to effort. It lent a fresh impulse to thought. It opened a channel for the widespread public interest which was gathering towards astronomical subjects to flow in. Much of this interest was due to the occurrence of events calculated to arrest the attention and excite the wonder of the uninitiated. The predicted return of Halley's comet in 1759 verified, after an unprecedented fashion, the computations of astronomers. It deprived such bodies forever of their portentous character. It ranked them as denizens of the solar system. Again, the transits of Venus in 1761 and 1769 were the first occurrences of the kind since the awakening of science to their consequence. Imposing preparations, journeys to remote and hardly accessible regions, official expeditions, international communications, all for the purpose of observing them to the best advantage, brought their high significance vividly to the public consciousness, a result aided by the facile pen of Lalande in rendering intelligible the means by which these elaborate arrangements were to issue in an accurate knowledge of the sun's distance. Lastly, Herschel's discovery of Uranus, March 13, 1781, had the surprising effect of utter novelty. Since the human race had become acquainted with the company of the planets, no addition had been made to their number. The event thus broke with the immemorable traditions, and seemed to show astronomy as still young and full of unlooked-for possibilities. Further popularity accrued to the science from the sequel of a career so strikingly opened. Herschel's huge telescopes, his detection by their means of 2 Saturnian and as many Uranian moons, his piercing scrutiny of the sun, picturesque theory of its construction, and sagest indication of the route pursued by it through space, his discovery of stellar revolving systems, his bold soundings of the universe, his grandiose ideas, and the elevated yet simple language in which they were conveyed, formed a combination powerfully effective to those least susceptible of new impressions. Nor was the evoked enthusiasm limited to the British Isles. In Germany, Schröter followed, longo intervallo, in Herschel's track. Von Zach set on foot from Gotha that general communication of ideas which gives life to a forward movement. Bode wrote much and well for unlearned readers. Lalande, by his popular lectures and treatises, helped to form an audience which Laplace himself did not disdain to address in the Exposition du Système du Monde. The great accession of public interest gave the impulse to the extraordinarily rapid progress of astronomy in the 19th century. Official patronage combined with individual zeal sufficed for the elder branches of the science. A few well-endowed institutions could accumulate the materials needed by a few isolated thinkers for the constructions of theories of wonderful beauty and elaboration, yet precluded by their abstract nature from winning general applause. But the new physical astronomy depends for its prosperity upon the favour of the multitude whom its striking results are well fitted to attract. It is, in a special manner, the science of amateurs. It welcomes the most unpretending cooperation. There is no one, with a true eye and a faithful hand, but can do good work in watching the heavens. And, not unfrequently, prizes of discovery which the most perfect appliances fail to grasp, have fallen to the share of ignorant or ill-provided assiduity. Observers, accordingly, have multiplied. Observatories have been founded in all parts of the world. Associations have been constituted for mutual help and counsel. A formal astronomical congress met in 1789 at Gotha, then under Duke Ernest II, and von Zach, the focus of German astronomy, and instituted the combined search for the planets suspected to revolve undiscovered between the orbs of Mars and Jupiter. The Astronomical Society of London was established in 1820, and the similar German institution in 1863. Both have been highly influential in promoting the interests, local and general, of the science they are devoted to forward, while functions corresponding to theirs have been discharged elsewhere by older or less specially constituted bodies, and new ones of more popular character are springing up on all sides. Modern facilities of communications have helped to impress more deeply upon modern astronomy its associative character. The electric telegraph gives a certain ubiquity which is invaluable to an observer of the skies. With the help of a wire, a battery, and a code of signals, he sees whatever is visible from any portion of our globe, depending, however, upon other eyes than his own, and so entering as a unit into a widespread organisation of intelligence. The press, again, has been a potent agent of cooperation. It has mainly contributed to unite astronomers all over the world into a body animated by the single aim of collecting particulars in their special branch for what Bacon termed a history of nature, eventually to become interpreted according to the sagacious insight of some one among them gifted above his fellows. The first really effective astronomical periodical was the Leech Correspondence, started by von Zach in the year 1800. It was followed in 1822 by Astronomische Nachrichten, and later by the Memoirs and Monthly Notes of the Astronomical Society, and by the host of varied publications which now, in every civilized country, communicate the discoveries made by astronomy to divers classes of readers, and so incalculably quicken the current of its onward flow. Public favour brings in its train material resources. It is represented by the individual enterprise, and finds expression in an ample liberality. The first regular observatory in the southern hemisphere was founded at Parramatta by Sir Thomas MacDougall Brisbane in 1821. The Royal Observatory at the Cape of Good Hope was completed in 1829. Similar establishments were set up to work by the East India Company at Madras, Bombay and St Helena during the first third of the 19th century. The organisation of astronomy in the United States of America was due to a strong wave of popular enthusiasm. In 1825, John Quincy Adams vainly urged upon Congress the foundation of a national observatory. But in 1843, the lectures on celestial phenomenon of Ormsby McCate Mitchell stirred an impressionable audience to the pitch of providing him with the means of erecting at Cincinnati the first astronomical establishment worthy of the name in that great country. On the 1st of January 1882, no less than 145 were active within its boundaries. The apparition of the Great Comet of 1843 gave an additional fillip to the movement. To the excitement caused by it, the Harvard College Observatory, called the American Pulkowa, directly owed its origin, and the example was not ineffective elsewhere. The United States Naval Observatory was built in 1844, Lieutenant Maury being its first director. Corporations, universities, municipalities vied with each other in the creation of such institutions. Private subscriptions poured in. Emissaries were sent to Europe to purchase instruments and to procure instruction in their use. In a few years, the young republic was, in point of astronomical efficiency, at least on a level with countries where the science had been fostered since the dawn of civilization. A vast widening of the scope of astronomy has accompanied, and in part occasioned, the great extension of its area of cultivation which our age has witnessed. In the last century its purview was a comparatively narrow one. Problems lying beyond the range of the solar system were almost unheeded, because they seemed inscrutable. Herschel first showed the sidereal universe as accessible to investigation, and thereby offered to science new worlds, majestic, manifold, infinitely infinite, to our apprehension in number, variety, and extent, for future conquest. Their gradual appropriation has absorbed, and will long continue to absorb, the powers for which it has served to develop. But this is not the only direction in which astronomy has enlarged, or rather has levelled, its boundaries. The unification of the physical sciences is perhaps the greatest intellectual feat of recent times. The process has included astronomy so that, like Bacon, she may now be said to have taken all knowledge of that kind for her province. In return, she prefers potent aid for its increase. Every comet that approaches the sun is the scene of experiments in the electrical illumination of rarefied matter, performed on a huge scale for our benefit. The sun, stars, and nebulae form so many celestial laboratories where the nature and the mutual relations of the chemical elements may be tried by more stringent tests than sublunary conditions afford. The laws of terrestrial magnetism can be completely investigated only with the aid of concurrent study of the face of the sun. The solar spectrum will perhaps one day, by its recurrent modifications, tell us something of the impending droughts, famines, and cyclones. Astronomy generalizes the results of the other sciences. She exhibits the laws of nature working over a wider area, and under more varied conditions than ordinary experience presents. Ordinary experience, on the other hand, has become indispensable to her progress. She takes in at one view the indefinitely great and the indefinitely little, the mutual revolutions of the stellar multitude during the tracts of time which seem to lengthen out to eternity as the mind attempts to traverse them. She does not admit to be beyond her ken, nor is she indifferent to the constitution of the minutest atom of matter that thrills the ether into light. How she entered upon this vastly expanded inheritance, and how so far she has dealt with it, is attempted to be set forth within the ensuing chapters. End of Preface and Introduction.
Chapter 1, Part 1 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 1, Progress of Astronomy During the First Half of the 19th Century. Chapter 1, Foundation of Sidereal Astronomy. Part 1. Until nearly 100 years ago, the stars were regarded by practical astronomers mainly as a number of convenient fixed points by which the motions of the various members of the solar system could be determined and compared. Their recognized function, in fact, was that of milestones on the great celestial highway traversed by the planets, as well as on the byways of space occasionally pursued by comets. Not that curiosity as to their nature and even conjecture as to their origin were at any period absent. Both were from time to time powerfully stimulated by the appearance of startling novelties in a region described by philosophers as incorruptible or exempt from change. The catalogue of Hipparchus probably, and certainly that of Tycho Brahe some 17 centuries later, owed each its origin to the temporary blaze of a new star. The general aspect of the skies was thus, however imperfectly, recorded from age to age, and with improved appliances the enumeration was rendered more and more accurate and complete, but the secrets of the stellar sphere remained inviolate. In a qualified, though very real sense, Sir William Herschel may be called the founder of sidereal astronomy. Before his time some curious facts had been noted, and some ingenious speculations hazarded, regarding the condition of the stars, but not even the rudiments of systematic knowledge had been acquired. The facts ascertained can be summed up in a very few sentences. Giordano Bruno was the first to set the suns of space in motion, but in imagination only. His daring surmise was, however, confirmed in 1718, when Halley announced that Sirius, Aldebaran, Betelgeuse, and Arcturus had unmistakably shifted their quarters in the sky since Ptolemy assigned their places in his catalogue. A similar conclusion was reached by J. Cassini in 1738 from a comparison of his own observations with those made at Cayenne by Richet in 1672. And Tobias Mayer drew up in 1756 a list showing the direction and amount of about 57 proper motions, founded on star places determined by Olaus Römer 50 years previously. Thus the stars were no longer regarded as fixed, but the question remained whether the movements perceived were real or only apparent, and this it was not yet found possible to answer. Already in the previous century the ingenious Robert Hooke had suggested an alteration of the very system of the sun, to account for certain suspected changes in stellar positions. Bradley in 1748 and Lambert in 1761 pointed out that such apparent displacements, by that time well ascertained, were in all probability a combined effect of motions both of sun and stars, and Mayer actually attempted the analysis, but without result. On the 13th of August, 1596, David Fabricius, an unprofessional astronomer in East Friesland, saw in the neck of the Whale a star of the third magnitude, which by October had disappeared. It was nevertheless visible in 1603, when Bayer marked it in his catalogue with the Greek letter omega, and was watched in 1638-39 through its phases of brightening and apparent extinction by a Dutch professor named Halwarda. From Hevelius, this first known periodical star received the name of Mira, or the Wonderful, and Boulliud in 1667 fixed the length of its cycle of change at 334 days. It was not a solitary instance. A star in the Swan was perceived by Janssen in 1600 to show fluctuations of light, and Montanari found in 1669 that Algol in Perseus shared the same peculiarity to a marked degree. Altogether the class embraced in 1782 half a dozen members. When it is added that a few star couples have been noted in singularly, but it was supposed accidentally, close juxtaposition, and that the failure of repeated attempts to measure stellar parallaxes pointed to distances at least 400,000 times that of the earth from the sun, the picture of sidereal science, when the last quarter of the 18th century began, is practically complete. It included 3 items of information: that the stars have motions, real or apparent, that they are immeasurably remote, and that a few shine with a periodically variable light. Nor were these scantily collected facts ordered into any promise of further development. They lay at once isolated and confused before the inquirer. They needed to be both multiplied and marshalled, and it seemed as if centuries of patient toil must elapse before any reliable conclusions could be derived from them. The sidereal world was thus the recognized domain of far-reaching speculations, which remained wholly uncramped by systematic research until Herschel entered upon his career as an observer of the heavens. The greatest of modern astronomers was born at Hanover, November 15, 1738. He was the 4th child of Isaac Herschel, a hautboy player in the band of the Hanoverian Guard, and was early trained to follow his father's profession. On the termination, however, of the disastrous campaign of 1757, his parents removed him from the regiment, there is reason to believe, in a somewhat unceremonious manner. Technically, indeed, he incurred the penalties of desertion, remitted, according to the Duke of Sussex's statement to Sir George Airy, by a formal pardon handed to him personally by George III on his presentation in 1782. At the age of 19, then, his military service having lasted 4 years, he came to England to seek his fortune. Of the life of struggle and privation which ensued, little is known beyond the circumstances that in 1760 he was engaged in training the regimental band of the Durham militia, and that in 1765 he was appointed organist at Halifax. In the following year he removed to Bath as oboist in Linley's orchestra, and in October 1767 was promoted to the post of organist in the Octagon Chapel. The tide of prosperity now began to flow for him. The most brilliant and modish society in England was at that time to be met at Bath, and the young Hanoverian quickly found himself a favourite and the fashion in it. Engagements multiplied upon him. He became director of the public concerts. He conducted oratorios, engaged singers, organized rehearsals, composed anthems, chants, choral services, besides undertaking private tuitions at times amounting to 35 or even 38 lessons a week. He, in fact, personified the musical activity of a place then eminently and energetically musical. But these multifarious avocations did not take up the whole of his thoughts. His education, notwithstanding the poverty of his family, had not been neglected, and he had always greedily assimilated every kind of knowledge that came in his way. Now that he was a busy and a prosperous man, it might have been expected that he would run on in the deep professional groove laid down for him. On the contrary, his passion for learning seemed to increase with the diminution of the time available for its gratification. He studied Italian, Greek, mathematics. Maclaurin's fluxions served to unbend his mind. Smith's harmonics and optics and Ferguson's astronomy were the nightly companions of his pillow. What he read stimulated without satisfying his intellect. He desired not only to know, but to discover. In 1772 he hired a small telescope, and through it caught a preliminary glimpse of the rich and varied fields in which for so many years he was to expatiate. Henceforward the purpose of his life was fixed. It was to obtain a knowledge of the construction of the heavens, and this sublime ambition he cherished to the end. A more powerful instrument was the first desideratum, and here his mechanical genius came to his aid. Having purchased the apparatus of a Quaker optician, he set about the manufacture of specula with a zeal which seemed to anticipate the wonders they were to disclose to him. It was not until 15 years later that his grinding and polishing machines were invented, so the work had at that time to be entirely done by hand. During this tedious and laborious process, which could not be interrupted without injury, and lasted on one occasion 16 hours, his strength was supported by morsels of food put into his mouth by his sister, and his mind amused by her reading aloud to him the Arabian Nights, Don Quixote, or other light works. At length, after repeated failures, he found himself provided with a reflecting telescope, a 5½ Gregorian of his own construction. A copy of his first observation with it on the great nebula in Orion, an object of continual amazement and assiduous inquiry to him, is preserved by the Royal Society. It bears the date March 4, 1774. In the following year he executed his first review of the heavens, memorable chiefly as an evidence of the grand and novel conceptions which already inspired him, and of the enthusiasm with which he delivered himself up to their guidance. Overwhelmed with professional engagements, he still contrived to snatch some moments for the stars, and between the acts at the theatre was often seen running from the harpsichord to his telescope, no doubt with that uncommon precipitancy which accompanied all his actions. He now rapidly increased the power and perfection of his telescopes. Mirrors of 7, 10, even 20 feet focal length were successively completed, and unprecedented magnifying powers were employed. His energy was unceasing, his perseverance indomitable. In the course of 21 years, no less than 430 parabolic specula left his hands. He had entered upon his 42nd year when he sent his first paper to the Philosophical Transactions. Yet during the ensuing 39 years his contributions, many of them elaborate treatises, numbered 69, forming a series of extraordinary importance to the history of astronomy. As a mere explorer of the heavens, his labours were prodigious. He discovered 2,500 nebulae, 806 double stars, passed the whole firmament in review for several times, counted the stars in 3,400 gauge fields, and executed a photometric classification of the principal stars, founded on an elaborate and the first systematically conducted investigation of their relative brightness. He was as careful and patient as he was rapid, spared no time, and omitted no precaution to secure accuracy in his observations. Yet in one night he would examine singly and attentively up to 400 separate objects. The discovery of Uranus was a mere incident of the scheme he had marked out for himself, a fruit gathered, as it were, by the way. It formed, nevertheless, the turning point in his career. From a star-gazing musician he was at once transformed into an eminent astronomer. He was relieved from the drudgery of a toilsome profession and installed as royal astronomer, with a modest salary of £200 a year. Funds were provided for the construction of the 40-foot reflector, from the great space-penetrating power of which he expected unheard-of revelations. In fine, his future work was not only rendered possible, but it was stamped as authoritative. On Whit Sunday, 1782, William and Caroline Herschel played and sang in public for the last time in St. Margaret's Chapel, Bath. In August of the same year the household was moved to Datchet, near Windsor, and on April 3, 1786, to Slough. Here happiness and honours crowded on the fortunate discoverer. In 1788 he married Mary, only child of James Baldwin, a merchant of the city of London, and widow of Mr. John Pitt, a lady whose domestic virtues were enhanced by the possession of a large jointure. The fruit of their union was one son, of whose work, the worthy sequel of his father's, we shall have to speak further on. Herschel was created a knight of the Hanoverian Guelphic order in 1816, and in 1821 he became the first president of the Royal Astronomical Society, his son being its first foreign secretary. But his health had now for some years been failing, and on August 25, 1822, he died at Slough in the 84th year of his age, and was buried in Upton churchyard. His epitaph claims for him the lofty praise of having burst the barriers of heaven. Let us see in what sense this is true. The first to form any definite idea as to the constitution of the stellar system was Thomas Wright, the son of a carpenter living at Byers Green near Durham. With him originated what has been called the grindstone theory of the universe, which regarded the Milky Way as the projection on the sphere of a stratum or disk of stars, our sun occupying a position near the centre, similar in magnitude and distribution to the lucid orbs of the constellations. He was followed by Kant, who transcended the views of his predecessor by assigning to nebulae the position they long continued to occupy, rather on imaginative than scientific grounds, of island universes, external to and coequal with the galaxy. Johann Heinrich Lambert, a tailor's apprentice from Mulhausen, followed, but independently. The conceptions of this remarkable man were grandiose, his intuitions bold, his views on some points a singular anticipation of subsequent discoveries. The sidereal world presented itself to him as a hierarchy of systems, starting from the planetary scheme, rising to throngs of suns within the circuit of the Milky Way, the ecliptic of the stars, as he phrased it, expanding to include groups of many Milky Ways, these again combining to form the unit of a higher order of assemblage, and so onwards and upwards until the mind reels and sinks before the immensity of the contemplated creations. Thus everything revolves, the earth round the sun round the centre of his system, this system round a centre common to it with other systems, this group, this assemblage of systems round a centre which is common to it with other groups of the same kind, and where shall we have done? The stupendous problem thus speculatively attempted, Herschel undertook to grapple with experimentally. The upshot of this memorable inquiry was the inclusion, for the first time, within the sphere of human knowledge, of a connected body of facts, and inferences from facts, regarding the sidereal universe; in other words, the foundation of what may properly be called a science of the stars. Tobias Mayer had illustrated the perspective effects which must ensue in the stellar sphere from a translation of the solar system, by comparing them to the separating in front and closing up behind of trees in a forest to the eye of an advancing spectator; but the appearances which he thus correctly described he was unable to detect. By a more searching analysis of a smaller collection of proper motions, Herschel succeeded in rendering apparent the very consequences foreseen by Mayer. He showed, for example, that Arcturus and Vega did in fact appear to recede from, and Sirius and Aldebaran to approach each other by very minute amounts, and with a striking effort of divinatory genius placed the apex or point of direction of the sun's motion close to the star Lambda in the constellation Hercules, within a few degrees of the spot indicated by later and indefinitely more refined methods of research. He resumed the subject in 1805, but though employing a more rigorous method, was scarcely so happy in his result. In 1806 he made a preliminary attempt to ascertain the speed of the sun's journey, fixing it by doubtless much too low an estimate at about 3 miles a second. Yet the validity of his general conclusion as to the line of solar travel, though long doubted, has been triumphantly confirmed. The question as to the secular parallax of the fixed stars was in effect answered. With their annual parallax, however, the case was very different. The search for it had already led Bradley to the important discoveries of the aberration of light and the nutation of the earth's axis. It was now about to lead Herschel to a discovery of a different, but even more elevated character. Yet in neither case was the object primarily sought attained. From the very first promulgation of the Copernican theory, the seeming immobility of the stars had been urged as an argument against its truth, for if the earth really travelled in a vast orbit round the sun, objects in surrounding space should appear to change their positions, unless their distances were on a scale which, to the narrow ideas of the universe then prevailing, seemed altogether extravagant. The existence of such apparent or parallactic displacements was accordingly regarded as the touchstone of the new views, and their detection became an object of earnest desire to those interested in maintaining them. Copernicus himself made the attempt, but with his triquetrum, a jointed wooden rule with the divisions marked in ink, constructed by himself, he was hardly able to measure angles of 10 minutes, far less fractions of a second. Galileo, a more impassioned defender of the system, strained his ears, as it were, from Arcetri, in his blind and sorrowful old age, for news of a discovery which 2 more centuries had still to wait for. Hooke believed he had found a parallax for the bright star in the head of the Dragon, but was deceived. Bradley convinced himself that such effects were too minute for his instruments to measure. Herschel made a fresh attempt by a practically untried method. It is a matter of daily experience that 2 objects situated at different distances seem to a beholder in motion to move relatively to each other. This principle Galileo, in the third of his dialogues on the systems of the world, proposed to employ for the determination of stellar parallax. For 2 stars lying apparently close together, but in reality separated by a great gulf of space, must shift their mutual positions when observed from opposite points of the earth's orbit, or rather the remoter forms a virtually fixed point, to which the movements of the other can be conveniently referred. By this means complications were abolished, more numerous and perplexing than Galileo himself was aware of, and the problem was reduced to one of simple micrometrical measurement. The double star method was also suggested by James Gregory in 1675, and again by Wallace in 1693. Huygens first, and afterwards Dr. Long of Cambridge, about 1750, made futile experiments with it, and it eventually led, in the hands of Bessel, to the successful determination of the parallax of 61 Cygni. Its advantages were not lost upon Herschel. His attempt to assign definite distances to the nearest stars was no isolated effort, but part of the settled plan upon which his observations were conducted. He proposed to sound the heavens, and the first requisite was a knowledge of the length of his sounding line. Thus it came about that his special attention was early directed to double stars. "I resolved," he writes, "to examine every star in the heavens with the utmost attention and a very high power, that I might collect such materials for this research as would enable me to fix my observations upon those that would best answer my end. The subject has already proved so extensive, and still promises so rich a harvest to those who are inclined to be diligent in the pursuit, that I cannot help inviting every lover of astronomy to join with me in observations that must inevitably lead to new discoveries. The first result of these inquiries was a classed catalogue of 269 double stars presented to the Royal Society in 1782, followed, after 3 years, by an additional list of 434. In both these collections, the distances separating the individuals of each pair were carefully measured, and with a few exceptions, the angles made with the hour circle by the lines joining their centres, technically called angles of position, were determined with the aid of a revolving wire micrometer specially devised for the purpose. Moreover, an important novelty was introduced by the observation of the various colours visible in the star couples, the singular and vivid contrasts of which were now for the first time described. Double stars were at that time supposed to be a purely optical phenomenon. Their components, it was thought, while in reality indefinitely remote from each other, were brought into fortuitous contiguity by the chance of lying nearly in the same line of sight from the earth. Yet Bradley had noticed a change of 30 degrees between 1718 and 1759 in the position angle of the two stars forming Castor, and was thus within a hair's breadth of the discovery of their physical connection. While the Reverend John Mitchell, arguing by the doctrine of probabilities, wrote as follows in 1767: "It is highly probable in particular, and next to a certainty in general, that such double stars as appear to consist of two or more stars placed very near together do really consist of stars placed near together and under the influence of some general law." And in 1784, "It is not improbable that a few years may inform us that some of the great number of double, triple stars, etc., which have been observed by Mr. Herschel, are systems of bodies revolving about each other." This remarkable speculative anticipation had a practical counterpart in Germany. Father Christian Mayer, a Jesuit astronomer at Mannheim, set himself in January 1776 to collect examples of stellar pairs, and shortly after published the supposed discovery of satellites to many of the principal stars. But his observations were neither exact nor prolonged enough to lead to useful results in such an inquiry. His disclosures were derided, his planet stars treated as results of hallucination. "On n'a point cru à des choses aussi extraordinaires," wrote Lalande, within 1 year of a better grounded announcement to the same effect. Herschel at first shared the general opinion as to the merely optical connection of double stars. Of this the purpose for which he made his collection is in itself sufficient evidence, since what may be called the differential method of parallaxes depends, as we have seen, for its efficacy upon disparity of distance. It was much too soon, he declared in 1782, to form any theories of small stars revolving round large ones, while in the year following he remarked that the identical proper motions of the two stars forming to the naked eye the single bright orb of Castor could only be explained as both equally due to the systematic parallax caused by the sun's movement in space, plainly showing that the notion of a physical tie compelling the two bodies to travel together had not as yet entered into his speculations. But he was eminently open to conviction, and had, moreover, by observations unparalleled in amount as well as in kind, prepared ample materials for convincing himself and others. In 1802 he was able to announce the fact of his discovery, and in the 2 ensuing years to lay in detail before the Royal Society proofs, gathered from the labours of a quarter of a century, of orbital revolution in the case of as many as 50 double stars, henceforth he declared to be held as real binary combinations, intimately held together by the bond of mutual attraction. The fortunate preservation in Dr. Maskelyne's notebook of a remark made by Bradley about 1759 to the effect that the line joining the components of Castor was an exact prolongation of that joining Castor with Pollux, added 18 years to the time during which the pair were under scrutiny, and confirmed the evidence of change afforded by more recent observations. Approximate periods were fixed for many of the revolving suns: for Castor 342 years, for Gamma Leonis 1200, Delta Serpentis 375, Sigma Bootis 1681 years. Sigma Lyrae was noted as a double star, a change of relative situation having been detected in each of the two pairs composing the group, and the occultation was described of one star by another in the course of their mutual revolutions, as exemplified in 1795 by the rapidly circulating system of Zeta Hercules. Thus, by the sagacity and perseverance of a single observer, a firm basis was at last provided upon which to raise the edifice of sidereal science. The analogy long presumed to exist between the mighty star of our system and the bright points of light spangling the firmament was shown to be no fiction of the imagination, but a physical reality. The fundamental quality of attractive power was proved to be common to matter so far as the telescope was capable of exploring, and law, subordination, and regularity to give testimony of supreme and intelligent design, no less in those limitless regions of space than in our narrow terrestrial home. The discovery was emphatically, in Arago's phrase, one with a future, since it introduced the element of precise knowledge where more or less probable conjecture had previously held almost undivided sway, and precise knowledge tends to propagate itself and advance from point to point. End of Chapter 1, Part 1. Chapter 1, Part 2 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Part 1, Chapter 1, Foundation of Sidereal Astronomy, Part 2. We have now to speak of Herschel's pioneering work in the skies, to explore with line and plummet the shining zone of the Milky Way, to delineate its form, measure its dimensions, and search out the intricacies of its construction was the primary task of his life, which he never lost sight of, and to which all his other investigations were subordinate. He was absolutely alone in this bold endeavour. Unaided, he had to devise methods, accumulate materials, and sift out results. Yet it may safely be asserted that all the knowledge we possess on this sublime subject was prepared, and the greater part of it anticipated, by him. The ingenious method of star gauging, and its issue in the delineation of the sidereal system as an irregular stratum of evenly scattered suns, is the best known part of his work. But it was in truth only a first rude approximation, the principle of which maintained its credit in the literature of astronomy a full half-century after its abandonment by its author. This principle was the general equality of star distribution. If equal portions of space really held equal numbers of stars, it is obvious that the number of stars visible in any particular direction would be strictly proportional to the range of the system in that direction, apparent accumulation being produced by real extent. The process of gauging the heavens, accordingly, consisted in counting the stars in successive telescopic fields, and calculating thence the depths of space necessary to contain them. The result of 3,400 such operations was the plan of the galaxy, familiar to every reader of an astronomical textbook. Widely varying evidence was, as might have been expected, derived from an examination of different portions of the sky. Some fields of view were almost blank, while others, in or near the Milky Way, blazed with the radiance of many hundred stars compressed into an area about one-fourth that of the full moon. In the most crowded parts, 116,000 were stated to have been passed in review within a quarter of an hour. Here the length of his sounding line was estimated by Herschel at about 497 times the distance of Sirius. In other words, the bounding orb, or farthest sun of the system in that direction, so far as could be seen with the 20-foot reflector, was thus inconceivably remote. But since the distance of Sirius, no less than of every other fixed star, was as yet an unknown quantity, the dimensions inferred for the galaxy were of course purely relative. A knowledge of its form and structure might, admitting the truth of the fundamental hypothesis, be obtained, but its real or absolute size remained altogether undetermined. Even as early as 1785, however, Herschel perceived traces of a tendency which completely invalidated the supposition of any approach to an average uniformity of distribution. This was the action of what he called a clustering power in the Milky Way. Many gathering clusters were already discernible to him even while he endeavored to obtain a true mean result, on the assumption that each star in space was separated from its neighbours as widely as the sun from Sirius. It appears, he wrote in 1789, that the heavens consist of regions where suns are gathered into separate systems, and in certain assemblages he was able to trace a course or tide of stars setting towards a centre, denoting not doubtfully the presence of attractive forces. 13 years later he described our sun and his constellated companions as surrounded by a magnificent collection of innumerable stars called the Milky Way, which must occasion a very powerful balance of opposite attractions to hold the intermediate stars at rest. For though our sun and all the stars we see may truly be said to be in the plane of the Milky Way, yet I am now convinced, by a long inspection and continued examination of it, that the Milky Way itself consists of stars very differently scattered from those which are immediately about us. This immense aggregation, he added, is by no means uniform. Its component stars show evident signs of clustering together into many separate allotments. The following sentences, written in 1811, contain a definite retraction of the view frequently attributed to him. I must freely confess, he says, that by continuing my sweeps of the heavens, my opinion of the arrangement of the stars and their magnitudes and of some other particulars has undergone a gradual change, and indeed, when the novelty of the subject is considered, we cannot be surprised that many things formerly taken for granted should on examination prove to be different from what they were generally, but incautiously, supposed to be. For instance, an equal scattering of the stars may be admitted in certain calculations, but when we examine the Milky Way, or the closely compressed clusters of stars of which my catalogues have recorded so many instances, this supposed equality of scattering must be given up. Another assumption, the fallacy of which he had not the means of detecting since become available, was retained by him to the end of his life. It was that the brightness of a star afforded an approximate measure of its distance. Upon this principle he founded in 1817 his method of limiting apertures, by which two stars brought into view in two precisely similar telescopes were equalized by covering a certain portion of the object glass collecting the more brilliant rays. The distances of the orbs compared were then taken to be in the ratio of the reduced to the original apertures of the instruments with which they were examined. If indeed the absolute lustre of each were the same, the result might be accepted with confidence. But since we have no warrant for assuming a standard star to facilitate our computations, but much reason to suppose an indefinite range, not only of size but of intrinsic brilliancy, in the suns of our firmament, conclusions drawn from such a comparison are entirely worthless. In another branch of sidereal science, besides that of stellar aggregation, Herschel may justly be styled a pioneer. He was the first to bestow serious study on the enigmatical objects known as nebulae. The history of the acquaintance of our race with them is comparatively short. The only one recognized before the invention of the telescope was that in the girdle of Andromeda, certainly familiar in the middle of the 10th century to the Persian astronomer Abdurrahman al-Sufi, and marked with dots on Spanish and Dutch constellation charts of the 14th and 15th centuries. Yet so little was it noticed that it might practically be said, as far as Europe is concerned, to have been discovered in 1612 by Simon Marius, mayor of Genzenhausen, who aptly described its appearance as that of a candle shining through horn. The first mention of the great Orion nebula is by a Swiss Jesuit named Cysatus, who succeeded Father Scheiner in the chair of mathematics at Ingolstadt. He used it, apparently without any suspicion of its novelty, as a term of comparison for the comet of December 1618. A novelty, nevertheless, to astronomers it still remained in 1656, when Huygens discerned, as it were, an hiatus in the sky, affording a glimpse of a more luminous region beyond. Halley, in 1716, knew of 6 nebulae, which he believed to be composed of a lucid medium diffused through the ether of space. He appears, however, to have been unacquainted with some previously noticed by Hevelius. Lacaille brought back with him from the Cape a list of 42, the first fruits of observation in southern skies, arranged in 3 numerically equal classes; and Messier, nicknamed by Louis XV. The ferret of comets, finding such objects a source of extreme perplexity in the pursuit of his chosen game, attempted to eliminate by methodizing them, and drew up a catalogue comprising in 1781 103 entries. These preliminary attempts shrank into insignificance when Herschel began to sweep the heavens with his giant telescopes. In 1786 he presented to the Royal Society a descriptive catalogue of 1,000 nebulae and clusters, followed 3 years later by a second of as many more, to which he added in 1802 a further gleaning of 500. On the subject of their nature his views underwent a remarkable change. Finding that his potent instruments resolved into stars many nebulous patches, in which no signs of such a structure had previously been discernible, he naturally concluded that resolvability was merely a question of distance and telescopic power. He was, as he said himself, led on by almost imperceptible degrees from evident clusters, such as the Pleiades, to spots without a trace of stellar formation, the gradations being so well connected as to leave no doubt that all these phenomena were equally stellar. The singular variety of their appearance was thus described by him: "I have seen," he says, "double and treble nebulae variously arranged, large ones with small seeming attendants, narrow but much extended lucid nebulae or bright dashes, some of the shape of a fan resembling an electric brush issuing from a lucid point, others of the cometic shape with a seeming nucleus in the centre, or like cloudy stars surrounded with a nebulous atmosphere. A different sort again contain a nebulosity of the milky kind, like that wonderful inexplicable phenomenon about Theta Orionis. while others shine with a fainter, mottled kind of light, which denotes their being resolvable into stars. These curious objects he considered to be no less than whole sidereal systems, some of which might well outvie our Milky Way in grandeur. He admitted, however, a wide diversity in condition as well as compass. The system to which our sun belongs he described as a very extensive branching congeries of many millions of stars, which probably owes its origin to many remarkably large as well as pretty closely scattered small stars that may have drawn together the rest. But the continued action of this same clustering power would, he supposed, eventually lead to the breaking up of the original majestic galaxy into 200 or 300 separate groups, already visibly gathering. Such minor nebulae, due to the decay of other branching nebulae similar to our own, he recognized by the score, lying, as it were, stratified in certain quarters of the sky. One of these nebulous beds, he informs us, is so rich that in passing through a section of it, in the time of only 36 minutes, I detected no less than 31 nebulae, all distinctly visible upon a fine blue sky. The stratum of Coma Berenices he judged to be the nearest to our system of such layers, nor did the marked aggregation of nebulae towards both poles of the circle of the Milky Way escape his notice. By a continuation of the same process of reasoning, he was enabled, as he thought, to trace the life history of nebulae from a primitive, loose, and extended formation, through clusters of gradually increasing compression, down to the kind named by him planetary, because of the defined and uniform discs which they present. These he regarded as very aged and drawing on towards a period of change or dissolution. This method of viewing the heavens, he concluded, seems to throw them into a new kind of light. They now are seen to resemble a luxuriant garden, which contains the greatest variety of productions in different flourishing beds. And one advantage we may at least reap from it is, that we can, as it were, extend the range of our experience to an immense duration. For, to continue the simile which I have borrowed from the vegetable kingdom, is it not almost the same thing whether we live successively to witness the germination, blooming, foliage, fecundity, fading, withering, and corruption of a plant, or whether a vast number of specimens, selected from every stage through which the plant passes in the course of its existence, be brought at once to our view? But already this supposed continuity was broken. After mature deliberation on the phenomena presented by nebulous stars, Herschel was induced in 1791 to modify essentially his original opinion. When I pursued these researches, he says, I was in the situation of a natural philosopher who follows the various species of animals and insects from the height of their perfection down to the lowest ebb of life. When arriving at the vegetable kingdom, he can scarcely point out to us the precise boundary where the animal ceases and the plant begins, and may even go so far as to suspect them not to be essentially different. But recollecting himself, he compares, for instance, one of the human species to a tree, and all doubt upon the subject vanishes before him. In the same manner we pass through gentle steps from a coarse cluster of stars such as the Pleiades, till we find ourselves brought to an object such as the nebula in Orion, where we are still inclined to remain in the once adopted idea of stars exceedingly remote and inconceivably crowded as being the occasion of that remarkable appearance. It seems, therefore, to require a more dissimilar object to set us right again. A glance like that of the naturalist, who casts his eye from the perfect animal to the perfect vegetable, is wanting to remove the veil from the mind of the astronomer. The object I have mentioned above is the phenomenon that was wanting for this purpose. View, for instance, the 19th cluster of my 6th class, and afterwards cast your eye on this cloudy star, and the result will be no less decisive than that of the naturalist we have alluded to. our judgment, I may venture to say, will be that the nebulosity about the star is not of a starry nature. The conviction thus arrived at of the existence in space of a widely diffused shining fluid, a conviction long afterwards fully justified by the spectroscope, led him into a field of endless speculation. What was its nature? Should it be compared to the coruscation of the electric fluid in the aurora borealis, or to the more magnificent cone of the zodiacal light? Above all, what was its function in the cosmos? And on this point he already gave a hint of the direction in which his mind was moving by the remark that this self-luminous matter seemed more fit to produce a star by its condensation than to depend on the star for its existence. This was not a novel idea. Tycho Brahe had tried to explain the blaze of the star of 1572 as due to a sudden concentration of nebulous material in the Milky Way, even pointing out the space left dark and void by the withdrawal of the luminous stuff. And Kepler, theorizing on a similar stellar apparition in 1604, followed nearly in the same track. But under Herschel's treatment, the nebular origin of stars first acquired the consistency of a formal theory. He meditated upon it long and earnestly, and in two elaborate treatises, published respectively in 1811 and 1814, he at length set forth the arguments in its favour. These rested entirely upon the principle of continuity. Between the successive classes of his assortment of developing objects, there was, as he said, perhaps not so much difference as would be in an annual description of the human figure were it given from the birth of a child till he comes to be a man in his prime. From diffused nebulosity, barely visible in the most powerful light-gathering instruments, but which he estimated to cover nearly 152 square degrees of the heavens, to planetary nebulae supposed to be already centrally solid, instances were alleged of every stage and phase of condensation. The validity of his reasoning, however, was evidently impaired by his confessed inability to distinguish between the dim rays of remote clusters and the milky light of true gaseous nebulae. It may be said that such speculations are futile in themselves and necessarily barren of results. But they gratify an inherent tendency of the human mind, and, if pursued in a becoming spirit, should be neither reproved nor disdained. Herschel's theory still holds the field, the testimony of recent discoveries with regard to it having proved strongly confirmatory of its principle, although not of its details. Strangely enough, it seems to have been propounded in complete independence of Laplace's nebular hypothesis as to the origin of the solar system. Indeed, it dated, as we have seen, in its first inception from 1791, while the French geometrician's view was not advanced until 1796. We may now briefly sum up the chief results of Herschel's long years of watching the heavens. The apparent motions of the stars had been disentangled, one portion being clearly shown to be due to a translation towards a point in the constellation Hercules of the sun and his attendant planets, while a large balance of displacement was left to be accounted for by real movements, various in extent and direction, of the stars themselves. By the action of a central force, similar to, if not identical with, gravity, suns of every degree of size and splendour, and sometimes brilliantly contrasted in colour, were seen to be held together in systems, consisting of 2, 3, 4, even 6 members, whose revolutions exhibited a wide range of variety, both in period and in orbital form. A new department of physical astronomy was thus created, and rigid calculation for the first time made possible within the astral region. The vast problem of the arrangement and relations of the millions of stars forming the Milky Way was shown to be capable of experimental treatment and of at least partial solution, notwithstanding the variety and complexity seen to prevail. to an extent previously undreamt of in the arrangement of that majestic system. The existence of a luminous fluid diffused through enormous tracts of space and intimately associated with stellar bodies was virtually demonstrated, and its place and use in creation attempted to be divined by a bold but plausible conjecture. Change on a stupendous scale was inferred or observed to be everywhere in progress. Periodical stars shone out and again decayed. Progressive ebbings or flowings of light were indicated as probable in many stars under no formal suspicion of variability. Forces were everywhere perceived to be at work, by which the very structure of the heavens themselves must be slowly but fundamentally modified. In all directions groups were seen to be formed or forming, tides and streams of suns to be setting towards powerful centres of attraction, new systems to be in process of formation, while effete ones hastened to decay or regeneration when the course appointed for them by infinite wisdom was run. And thus, to quote the words of the observer who had looked farther into space than ever human being did before him, the state into which the incessant action of the clustering power has brought the Milky Way at present is a kind of chronometer that may be used to measure the time of its past and future existence, and although we do not know the rate of going of this mysterious chronometer, it is nevertheless certain that, since the breaking up of the parts of the Milky Way affords a proof that it cannot last for ever, it equally bears witness that its past duration cannot be admitted to be infinite. End of Part 1. Chapter 1, Part 2.